So the math continues. We are going to be determining chemical formulas from experimental data in section 3.10. Alright, so the process here is to keep in mind that even though we make our experimental measurements in terms of mass, that what we're looking for in an empirical formula is a ratio of moles. And keep in mind the empirical formula, if we've forgotten that from way back in chapter 1 at this point, which is like a month ago, isn't it? It's crazy how time flies. The empirical formula is the simplest ratio, whole number ratio, of atoms. And we put that in a chemical formula. So just for instance, if we had C3H9, for instance, which probably doesn't actually really exist, but work with me here, the empirical formula for this molecule would be CH3. It's the simplest whole number ratio of these compounds, of these 3 and 9 ratios. Okay? Alright, so let's look at this idea. We have a liquid sample. We decompose it into its elements. It is found that the sample contained 0.857 grams of hydrogen and 6.86 grams of oxygen. So to figure out this ratio of moles, what we do is first we convert everything into moles. Okay, so hit the wrong button. So how do we do that? Well, we use the periodic table. 1.01 grams from the periodic table of hydrogen for every 1 mole. And of course, you see what I'm doing wrong here right away, right? I'm putting this the wrong direction. So 1 mole of hydrogen for every 1.01 grams of hydrogen means that we have, okay, grab the calculator, 0.857 divided by 1.01, and we get 0.849 moles of hydrogen. Good. And how many moles of oxygen do we have? We have 6.86 grams of oxygen. We look up the molecular, or the molar mass, I should say, of oxygen on the periodic table. Let's see, it's 16. And so now we take 6.86 times 1 divided by 16 and get 0.429 moles of oxygen. Okay, so we've converted everything into moles, so we can start making a comparison between these. So with those two numbers, what we get is H.849, O.429. Yeah, that's not a simple whole number ratio, right? Well, if we have ratios, how do we get whole number ratios, or at least closer to it? We use the smallest number to set up a ratio between the two. So we divide by that number in both instances. So we're going to divide both by 0.429 because that's the smallest number present here. Okay? So when we do that, what we're getting is 1.98 for hydrogen, and not surprisingly, the smallest one divided by itself is 1. At this point, you're going to have to make some logical assumptions. You're going to have to say this probably isn't H198 to O100, or whatever the simplest whole number ratio of that would be. What you're going to say is, experimentally, I'm pretty close here to H2O. So I'm just going to say this is H2O. Voila. So let's look at another example, but here we're using percentages. And some instrumentation that you use to measure elemental abundance will give you percentages for the different amounts. So same thing as before, but if we have percentages, our first step is going to instead be assume that we have 100 grams. Well, 60% of 100 grams is 60.00 grams of carbon. And 4.48% of 100, see why we're assuming 100, right? Is 4.48 grams of hydrogen. And of course, the same process tells us with 100 grams of sample, percent directly translates to grams. And there we go. So now that we've found this ratio, or this set of grams, we do the same thing we did before. So 60 grams of carbon, turn this into moles. That's our first step. And 4.48 grams of hydrogen will be turned into moles of hydrogen. And 35.52 grams of oxygen are going to put us into 1 mole of oxygen for every 16 grams. So let's figure out what that is. 60 divided by 12.01 is this darn close to 5. 4.996 moles of carbon. 4.48 divided by, oh my goodness, that's not the mass from the periodic table. It should be 1.01 grams. There we go. So we have 4.44 moles of hydrogen, and 35.52 divided by 16 gives us 2.220 moles of oxygen. Good. Peek ahead here. Nope. One more step here before we go on to the next slide. So what we have is C, 4.996, H, 4.44, O, 2.220. So, just like we did last time, divide everything by the smallest number. 2.220, 2.220, 2.220. And we get C, let's see, 4, 6 divided by 2.20, 2.25, H2O1. Alright, what do we do with this? We really can't say that experimentally 2.25 is just close enough to 2 and just be happy with it. So instead what we're going to have to do is now multiply up instead of divide down to get whole number ratios. And how can I get to a whole number ratio? Well, 0.25 is basically a quarter. It's a fourth. So if I multiply everything by 4, I can get to a whole number set of ratios. Okay, so 2.25 times 4 is 9. So C9. 2 times 4 is 8. So C8. 1 times 4 is 4. So C9H8O4 is our empirical formula. Now we can get the molecular formula very easily, actually, once we have the empirical formula, if by some other instrumental method, and there are several, we can get the molar mass of the compound. And we do that just by figuring out what multiple this molar mass is of the molar mass of the empirical formula. And so what that's basically saying is we have this C2H3O, and this will be multiplied by some number to give us the molecular formula. Right? Because the empirical formula was just the, divide out some whole number constant result of the molecular formula. So we just have to figure out what this number is. Well, what's the molar mass of C2H3O2? Okay, so 2 carbons times 12.01 grams per mole each. 3 hydrogens times 1.01 grams per mole each. And 1 oxygen times 16.00 grams per mole each. So we have 24.02, 3.03, and 16.00. And so this is the molar mass of the empirical formula. 4.02 plus 3.03 plus 16 gives us 43.05 grams per mole. All right, so all we do now is take the molar mass of the molecular formula, 86.09 grams per mole, and divide the empirical formula, molecular mass, by this, and we get 2. So this empirical formula will have to be multiplied by 2 to give us the molecular formula. So the molecular formula must be C4H6O2. And if we work this out, 4 carbons, 6 hydrogens, and 2 oxygens, we should get pretty close to this 86.09. There's one more type of analysis that does the same type of process to find the empirical formula, and that's combustion analysis. Now, what this is doing is this is taking some compound that contains carbon, hydrogen, and oxygen and burning it, which means chemically combining it with oxygen. And now all of the carbons will become carbons in carbon dioxide. All of the hydrogens will become hydrogens in water molecules, in water vapor. Now, how much oxygen I originally had, that you have to kind of figure out by inferring from the other portions that you determine. So how do we use this to get the empirical formula? Let's take a look at that. So let's say that we have an initial sample with a mass of 0.8233 grams. That's whatever this is. We burn it up with lots of oxygen. We don't know how much. And we get 2.445 grams of CO2 and 0.6003 grams of water. So let's make some comparisons. Let's find out how many moles of carbon I have in 2.44 grams, 5 grams of carbon dioxide. So 2.445 grams of CO2. So remember when we wanted to get amount of one of these parts, we had to turn this into moles first because that's our counting number. So we know we have 1 mole of CO2 for every, let's see, 12, 16, and 16 gives me 44.021 grams of carbon dioxide. All we did is go to the periodic table and add up carbon and 2 oxygens. And we also know that there's 1 carbon for every carbon dioxide. So this will cancel grams, will cancel moles of CO2, and we're left with moles of carbon. And where did all that carbon come from? It came from our original sample. Okay, so what do we get? 2.445 divided by 44.01 gives us 0.055, lots of 5s repeating here, moles of carbon. Good. Let's do the same thing with hydrogen. 6003 grams of water. Go to the periodic table and find the molar mass of water to be 18.02 grams for every 1 mole. And now keep in mind, 2 hydrogens for every 1 H2O means that our original compound provided us with 18.2 times 2, 0.06626 moles of hydrogen. All right, so far so good. But wait a minute, how much oxygen did we have? All right. Well, we know we had 0.8233 grams of this stuff before. If we could subtract off the carbon and subtract off the hydrogen grams, we'd be left with the oxygen grams that were just present in the original molecule, original sample. So let's figure out how many grams of carbon and grams of hydrogen we had. Well, we had 0.0555, etc. moles of carbon in the original sample. So that correlates with 0.6672 grams of carbon. All right. And we had 0.06626 moles of hydrogen. And we have 1.01 grams of hydrogen for every 1 mole. So that gives us, let's see, 0.06626 times 1.01, 0.0669 grams of hydrogen. And again, we're not really getting too into sig figs at the moment because we're not at our final answer. So that means between carbon and hydrogen, I can take the 0.8233 grams of carbon, hydrogen, and oxygen, subtract 0.6672 grams of carbon, and subtract 0.06692 grams of hydrogen. And what I'm left over with will be grams of oxygen in that original sample. All right, so 0.8233 minus 0.6672 minus 0.06692, and we get 0.08918 grams of oxygen in the original sample. If there wasn't any oxygen in the original sample, you'd get something darn close to 0 here, if not 0 itself. So if you get something at this point like 0.00015, there wasn't any oxygen in the original. That's just the experimental error. And that might be the case, but it wasn't here. So let's find out now how many moles, 0.08918 grams of oxygen. Right, this is in the initial sample. So how many moles does that correspond to? Because once we know the moles of everything in the original sample, that's how we go about getting our empirical formula, right? So 1 mole of oxygen for every 16.00 grams of oxygen gives us, let's see, that's something I got to type in the calculator, right? Divided by 16 gives us 0.005574. All right, I now know the moles of all 3 components, and I can set up a ratio. C, 0.05555, H, 0.06626, O, 0.005574. Well, we can guess which the smallest one is. We'll divide all 3 by the oxygen. So that's 0.055555, etc., divided by 0.005574. We get C 9.97. And let's divide hydrogen by the oxygen. So 0.06626 divided by 0.005574. We get 11.89. And now the oxygen, 0.00, well, 1. All right, so now again we use our logical deductive reasoning and say this must be C10, H more than likely 12, although that's a little bit dicey, but not really. 11.9, that's 12. O1. There's our empirical formula for this compound.